So welcome everybody to this last day for the first week of lectures. So this morning we will conclude the discussion on QCD and collider physics with Simone. So please, Simone.
Thank you, Giuliano. Good morning, everyone. So today I'll try to wrap up our discussion. And in order to do so, let me first go quickly through the things we said and hopefully try to give you an idea what was my aim for these lectures. I don't know if they turn out to be confusing, but at least this is what I did. So we started with some basics, facts about collider phenomenology. And from the point of view of the theory, we introduced the pattern model. So as a way to, it's the simplest way we have to describe high energy interactions in proton-proton collisions. And we kept, as an example, always this Brownian process. Then, in the second lecture, we try to ask ourselves if how we can incorporate QCD corrections to this simple picture. And we did so for the very inclusive lepton pairing baryon mass distribution. And we saw that although we encountered some infinities in our calculations, we can actually either show that they cancel when we add inclusively real and virtual corrections, or we can get rid of them through some sort of renormalization. UV singularities can be dealt with the renormalization of the Lagrangian parameters, and then we found these initial state collinear singularities that we can absorb into a redefinition of the particle densities, and this led to this famous set of equations, which are known as Lipatov alternative equations. Then we said, okay, can we try and be a little bit more differential? Can we measure the distribution, can we compute and measure the distribution of some observers? And in order to do that, we identify a key property from the point of view of the theory, which is infrared encollinear safety. And we analyze that by looking at matrix elements in the soft and collinear limit. So the soft limit I did it pretty fast. We concentrate on the collinear limit. Then yesterday we did a calculation of an actual observable, and we say we want to probe QCD dynamics, but we do so in an indirect way by looking at the transmomental of the Z boson. And we saw that if you want to describe this distribution also in the regime where there's an hierarchy of scales, where the PT, the transmomental of the Z boson, is much lower than the typical scale of the process set, the mass of the Z boson, or the invariant mass of the lepton pair, then fixed order perturbation theory is not enough, and we need to, because we think the calculation develops large logarithmic corrections, so we want to resum them to orders. And so we introduce these resummation techniques that allow us to account to all perturbative orders, although in a limited kinematic regime, these contributions. Then we move one step further and we say, okay, this is an indirect way of probing QCD radiation. Can we find observables that make sense, and meaning that they can be computed in perturbation theory, that directly probe QCD radiation? Now, we quickly realize that sort of computing cross-section distribution for particular hadrons, well, that's not an IRC safe thing to do. We will need the equivalent of particle distribution function, which I call fragmentation function. So, but however, we saw that we can introduce the concept of jets. And yesterday we had a very qualitative description of what jets are, why they emerge in perturbative QCD, and what are the definitions that we can actually employ. So in the final part, in the final lecture of this course, what I would like to do is to dig even more in detail. So we're not we don't want just to describe general properties of jets, but we really want to go inside the jet, we want to look inside the jet and try to understand its structure. And we'll see that this is interesting for many different reasons. And so the final lecture is dedicated to jet substructure, and I hope to convince you that it's it's still an exciting field of research, and something that it's worth spending time thinking about. As you will imagine, I'm fairly passionate about this topic. Okay, so let's talk about jet substructure. The way I want to do it is actually starting with a kind of historical detour. And so this is actually the way, one of the main reasons just structure was developed, but it's still, I think, one of the key motivation. So that's why I want to start with a bit of history. So I'll start saying something that has nothing to do with just structure, but has to do with Higgs physics. And the reason being that one of the main reasons, if not the main reason, the Large Hadron Collider was built is to discover the Higgs boson and to study this property. Phrased in a more elegant way, the Large Hadron Collider was built to study the mechanism of electroweak symmetry break. Okay, so we want to understand whether the Higgs mechanism was really the correct way of looking at electroweak symmetry break. And one of the features, so we discovered the Higgs boson, fine. I remember drinking champagne on that day. The sort of the program in Higgs physics at the IHC essentially started with that discovery and keeps aiming to try and assess as much as we can of the properties of the Higgs boson to really pin down whether this particle is responsible for electroweak symmetry breaking, and whether the simplest mechanism as drawn by Peter Higgs, Braut and Engler is really relies on nature. So one of the predictions, this you all know, of the standard model with the Higgs mechanism is that the Higgs through its vacuum explosion value gives rise to the elementary particle masses. And this happens, of course, for the gauge boson, because that's the electroweak symmetry breaking, but also happens for the fermions, because I remind you that the gauge group of the standard model has a SU2 chiral component, left component, and so we cannot write down Dirac mass terms for the fermions directly. So also for the fermions, we need to generate this mass through the break. And these two things have a spectacular consequence, which is something that we can actually test, and it's the fact that the coupling of the Higgs to any mass of the standard model should be proportional to the particle mass. In particular, this is true for the fermions, but also the coupling square for the gauge boson. And so that's a prediction of the standard model that we can test experimentally. And so that's why the Atlas and CMS collaborations often produce these plots where they show mass of the fermions. Let's do it for the fermions, and coupling to the Higgs. So they measure in some way. There are a way of determining the coupling of this particular particle, particular fermions that they want to study to the Higgs, and they can plot it against the fermion mass. And for instance, they can do this for the top, which is a very high mass, and they'll try to do this for the bottom and for the lighter states. And the prediction is that these, well, that's not what I want to say. And the prediction of the standard model is that these values should align on a straight line. Okay? So in order not to spoil the standard model, let's blink it's a little bit high. Okay? And indeed, like if you look at the actual data, this looks more or less the case. Of course, some of these error bars are fairly large, and so it's the job of the experimenter is to measure these things more and more precisely, so that we can really pin down whether there's a straight line that fits where it goes to those points. So one of the interesting thing about this feature is that we all know that the mass of the fermions, the mass of the quarks and the leptons, they span like many orders of magnitudes in the standard model. And of course, this immediately translates to this Yukawa coupling. So if we take the Yukawa coupling of the Higgs to the top, then you can measure, for instance, by looking at, well, you can do this either for the inclusive cross-section of associated production of the Higgs with TT bar. This is of order 1. The top mass is large, and so on. And if you take the electron instead, well, that's of order 10 to the minus 6. And so there's a huge hierarchy in the Yukawa couplings. And so one way of try to understand whether this is the case in the standard model is to measure from an experimental viewpoint, is to measure more and more precisely, for instance, the decay of the Higgs into fermions. Now, not all these channels are accessible in the LHC, as we'll see, and so that's why people are thinking to build so-called Higgs factories in Higgs plus and minus collision. So imagine you can, for instance, build a machine that produces on-shell Higgs in the same way that lab produce on-shell Z boson, and then you can really study at very high accuracy these branching fractions, and so try to see if the data tells you something about the underlying theory. Is there some pattern behind this flavor hierarchy? Okay, what can we do at the LHC? Well, let's start from, when you think, okay, let me look at the most likely of these decay rates. Well, the biggest Yukawa coupling is the top. However, an on-shell Higgs cannot decay into a top and top pair on-shell because of energy conservation. And so the second one we would like to look at is the second heaviest elementary fermions, which is the bottom quark. So the mass of the big quark is roughly 4.2 GeV. So definitely we can have Yukawa coupling is something like 10 to the minus 2, I don't know, 2 or 3 here. I don't know. So definitely there is phase space, plenty of phase space, and a fairly large Yukawa coupling, so that the decay is to be bar as possible. What is the downside of the LHC? Well, you put on your Pheno hat, and then say, okay, if I want to see a process, I need to ask myself, what are the backgrounds? So what are the processes that give rise to the same final state? So I see the same thing in the detector, but I need to disentangle signal to background. So for instance, at the LHC, for instance, I can produce the Higgs in fusion through an effective vertex, I produce the Higgs, and then I decay in dB bar. Okay, that's one possibility. What are the backgrounds? Well, the backgrounds, if I do nothing, well, all the backgrounds are all the possible ways I can produce a dB bar pair at the LHC. And well, QCD tells you that you have, for instance, these type of processes. Okay, and this background, the QCD background, is huge. And so that led to, some people say, this channel is dead at the LHC. This, like, 15, 20 years. Actually, no, we do see this channel with interesting background rejection techniques. But what the strategy I'm gonna try to present now is the strategy, the idea that actually gave rise to the Jepson structure revolution. And actually, what comes into rescue is something that we've seen already. So we would like to reduce the QCD background, reduce the imbalance between reduce the total QCD background. And one way of doing that is to require something that some electroweak probe in the final state. Because if we can, the key word, remember, is trigger. So if you can see events where we have, say, a B plus and minus pair, that allows me to discard like pure QCD BB bar production, because there's no million pair. Okay. So the idea that people have is that, okay, let's look at a more complicated process. For instance, QQ bar. Okay, I shouldn't talk about finiteness. For instance, like I can produce the Higgs in conjunction with an electroweak boson that then decays into BB bar. Okay, and if you think a little bit in the standard model, one way of realizing this is through this type of diagram. So I produce a Z boson, then decays into B plus and B minus, for instance. This will be an off-shell Z, otherwise I cannot conserve energy. And then this can be produced together with the Higgs, and the Higgs now can decay into B bar. You see now that I have hope, because it's true that I took a hard hit in the cross-section, because this cross-section is much lower than just producing the Higgs and then later decay to BB bar. But also, by requiring a mu plus mu minus pair, I fight a lot and I cut down the QCD background. So then, what are the features? Well, now, for instance, you see that the Higgs is always produced in conjunction with another particle. And so, for instance, we will have some transfer momentum. Now, what is the main background to this process? Well, I always will require a Z, so mu plus mu minus, and then I have the Higgs which decays into BB bar. So the most generic process I can think of will be Z plus jet. Actually, we could do better because there are experimental ways of saying, well, this jet actually contains B quarks. These techniques go under the name of V-tagging. This is a complicated matter, so I'm going to ignore in the discussion that follows that we can actually do B-tagging. So if you want the discussion I'm going to do in the following is a bit too simplistic, because we can actually do better if we require B-tagging. But let me, in order to get the important messages, B-tagging is not necessary. So if we have no way of saying, well, of recognizing B hadrons that originate from B quarks, then the honest thing that we can say is that, well, the background to this process is if the Z decay into mu plus mu minus, and then here I have two quarks which will fragment and give rise to jets. And so my background will be Z plus jets. That's where the jet structure revolution started. There were already papers before this famous one, I'm going to mention in a second, but really like talking about looking at the substructure of jets. But this subject really haven't really like taken off until 28, where there was a very famous paper by John Butterworth, Davidson, I don't remember his first name, Mathieu Rubin, and Gavin Saran. And in this paper, they propose to use jet structure to discover the Higgs at the LHC through these type of processes. Now, just a quick motivation for you, the D and the R in the previous paper were PhD students at the time. And so I was also a PhD student at the time, but I didn't practice it. Anyway, so this is a challenge for you to come out with the next paper that will give rise to a revolution. I mean in physics, not politics. So what is the proposal that sort of sparked this revolution? Well, the authors said, okay, let's take another heat index perception. So by requiring not only that the Z, that the Higgs is produced together with the Z, but I also want to really ask for a regime where the transmomentum of this guy, of the Higgs and the Z is very large. So I want to go into a regime where the transmomentum of the Z is fairly similar to the transmomentum of the Higgs. So the two things are balanced in terms of momentum, and it's large meaning much bigger than the Higgs mass. So what happens in this regime? Well, I have my proton coming in, they collide, and I produce a Z boson and a Higgs, and they decay. The Z boson will decay in mu plus mu minus, and the Higgs decays into BB bar. So what happens as the transfer momentum of these guys is increased? Well, because of kinematic, relativistic kinematic, the decay product will be more and more collimated along the boost directions. So if I have a very energetic particle that decays, so if I have a rest particle that decays, say a scalar particle that decays in its rest frame, the decay product will be distributed in a ferrocosmetic way. If instead I look at this particle in a boosted in a booster frame where this particle is moving very fast, then its decay product will tend to be collinated along the boost direction. And so the reason for going to this very high boost is that the decay products of the Z on one side, and more importantly, of the Higgs on the other side, will come closer and closer together. If they are close enough, then any jet element that you run to reconstruct the hadronic decay products will pick up these two guys as in one jet, as belonging to one jet. So you can imagine that if the Higgs decay is almost at rest, BB bar, they fly in opposite direction, they hadronize, and they form two jets, two or more jets. If the Higgs is boosted, then in the lab frame, these decay products become closer and closer, and eventually the jet element won't say two jets, but just one jet with all the decay products. And now all of a sudden, the background to this process is no longer Z plus jets, but is Z plus one jet. So I have this is one side, and on the other side, this is the background, and the background will be, so for instance, this. X plus one jet. Now, as I said, I can do better because I could require this jet to be B-typed, and so it will look a little bit different. But let's ignore this for a moment. So that's the key observation. So I can fight the combinatory background. So the fact that if I produce many jets, I don't know how to couple them, by really going to the booster regime. And the LHC is powerful enough that I have a lot of phase space to do so, and really comparing two big jets, try to distinguish whether they are signal jets, so originating from the Higgs, boosted Higgs decaying to BB bar, or the background jets, the QCD jets. What is the conditioning to satisfy? Well, let's do a very simple leading order calculation. I want a leading order. What I have is that I have Higgs that decays into BB bar. So I can do this in the, well, I call this Q, what am I call it, PB, P, and PB bar. So I know that Q square, regardless of the frame I'm evaluating, Q square is always mx square. In the narrow width approximation, the Higgs is produced on shell. But so m square is equal to PV plus PV bar all squared. So this will be mass of the Higgs plus, mass of the B squared plus mass of the B squared, but in the very high energy limit, I can neglect this. So this will be QB V bar. Okay, and how can I write this? Remember, so if the if I consider the B masses because I'm energetic enough, then this will be twice P. Theta. Now, and well, cos theta is the angle between B and B bar. So in the collinear limit, which is the one I'm interested in, if these guys are collimated, then I can write these roughly. So 1 minus cosine is roughly cos theta squared over 2. So this is roughly Z, 1 minus Z, PT of the Higgs square, theta square, theta BB bar square. Opening. Now, the Higgs decay into BB bar. So you can imagine to write down a splitting function also for the splitting. And one feature of a scalar decay into BB bar, a scalar decay into fermions, is that the splitting function is fairly trivial. It's essentially a constant, which you can normalize to 1. So what does it mean is that the B and the B bar will share the energy almost equally. So that most likely Z is equal to a half, because there's no, so if you were to do this type of splitting, then this type of splitting are enhanced in the region where the energy of the gluon is small. It's much smaller compared to the energy of the quark because of the way it's because of the soft enhancement. But Higgs to BB bar, that's the splitting function essentially U inside. And so this is we can write this as roughly a quarter beta Higgs theta square BB bar. And so you see that the if I want that the B and the B bar to be reconstructed in a jet of radius r, what I need to ask is that if I want the theta BB bar to be less than r, this is the condition so that the two B's are reconstructed in the same jet. What I have is that Higgs squared times 4 divided by PT Higgs squared should be less than r squared. And so I have to look at Higgs with transfer momentum bigger than twice Higgs mass over r, so if I want to reconstruct the decay product of the Higgs in one jet. And that's the sort of boost condition that I want to satisfy. So I will talk about this is a leading mode analysis. One can make it a little bit better by considering my orders. But when I have in mind the boosted regime, what I mean is that I want to produce an object with this, which has this relation with transfer momentum, which are bigger than twice the mass of the object I'm producing divided by the jet radius I'm considering. And we're discussing this for the Higgs, but you can apply very similar techniques to Z boson, W boson, and TOPS. Actually, historically, that's what we've done. So we started this, PDRS started this revolution in 2008, but really the first observation of Higgs to BB bar in this boosted regime is only like a 1 or 2 year old, maybe 1 year old. What people have been doing in the substructure community for 10 years is to develop better and better techniques and test them on easier particles, Z, W, and top quarks. And so that we can, this allows us to build like a set of tools which were powerful enough that could be then applied to Higgs physics or new physics, if that would turn out.
Sorry,
So,
I have a question. Can I?
Yeah, absolutely.
Yeah, no, I understand the point of view from the physics point of view, but what does it really mean to compare an angle with the radius in this case? I mean, we are considering an angle less than a radius, so.
Okay, yeah, sure. So there's one thing we can, well, what is the jet radius? Okay, so the jet radius is, we can look at jets in two ways. So if we look at the jets in our usual rapidity and angle, now a perfectly round jet will look like a circle in this rapidity, and the circle is related to the jet radius. So that's actually an interesting exercise that it's on the notes that you can do. So if you take any of the jet algorithm of the generalized KT families, the one with the P dependence, you can show that if you have a jet with two particles only, the condition for them to be reconstructed in one jet is that their distance in the azimuthal and rapidity plane should be less than r. So you can show that if you have only two particles, these are reconstructing into a jet if the distance delta in this plane is less than r. Now, another thing you can do in the Cornelian limit is that you can relate this distance in rapidity and azimuth to the angular separation between the three momenta of the two jets, of the two particles. And that's how I wrote down this. So you can also show that the you can look at the how can you do that? Well, for instance, you can write down the full momentum either in terms of angles, energy and angles, or in terms of rapidity and azimuth. And you can convince yourself that it really is the same thing to, so this is, if you want, is a projection in the y-phi plane, but you can also look at the free momentum of the particles. And this is the angle. And in the collinear limit, you see that requiring this angle to be smaller than r is the same as requiring that delta is smaller than r. Indeed, if you were to use define jet algorithm in a plus or minus collision, you usually use angles between the particles rather than these distances on the azimuth rotating.
Okay, so in this case, this r we are using some sort of dimensionless version of the radius in some sense.
It's always, I mean, the jet radius is always dimensions. It's a number. It's pure number.
Okay, okay, I see. Thanks.
Okay, any other question? Okay. So this is the game we're going to play. So we're going to go in the boosted regime where we show that we collect, well, we can talk about one jet as being the container of the decay product of the particle we're interested in. And we're going to try and distinguish this jet, signal jet, from the QCD bank, from a jet that originates from the QCD bank. Now, so we'll start simple. What is the most simple jet observable? What is the most simple jet properties that we can try and use to distinguish the signal jet from a background jet? And you think a little bit about that. There's a clear distinction between the two. The signal jet has an intrinsic mass scale, the mass of the particle that is decaying. Well, the background jet, the QCD jet, doesn't have this scale, the intrinsic scale. The only energy scale that QCD jet knows of is the transfer momentum of the jet. There is no mass scale in the QCD jet. And so that's the first thing we can try and exploit. So if we are able, let's think about parton level, then we can see how to generalize this model. So if we are able to really collect all the decay products of the Higgs, so now I'm considering not just the leading order 1 to 2 decay, but I let the B fragment, and so I produce many partons. But let's say I'm able to reconstruct them all, then the equality we wrote before still holds, because for momentum conservation in the narrow width approximation, what we'll have is that the momentum of the Higgs should equal the sum of the momenta. Well, it's always the case that the momentum of the Higgs should equal the sum of the momenta of its decay product. But if we look at the this boosted regime, what we can say is that if I sum the full momenta of all the particles in the jet I'm reconstructing, if the jet is defined in such a way that it's really picking up all the decay product, then I have this equality. And this equality immediately implies that the mass of the Higgs should be equal to the sum of I in the jet of all the full momentum of the jet square. And what is this? This is the jet invariant mass. So, I mean, in the limit where it's only the decay product, then the distribution of the jet mass at parton level is just a delta function picked at the mass of the Higgs. Now, of course, there are other effects. You can have QCD, you can have some leakage, you can have some initial state radiation that goes into your jet. So really what we expect at parton level is that if we look at the invariant mass distribution of my jet, this mass distribution should be picked around the jet mass, possibly with some tail. Sorry, I should label the axis. That is d sigma, the mj square, or the mj. And so very often we look at normalized distribution because we are interested in the shape. So a signal jet looks like that. or should look like that. At least apart now. Now, the question we will try to answer, hopefully before the break, is what does the background distribution look like? Background jets. So we say there is no intrinsic scale, so I don't know what to put here. So the question is like, what does it look like? And we're going to try and understand this, assuming that the jet is a pure QCD jet, so no B-type. So we already said that the only scale is the PT of the jet, and so the mass, the invariant mass of the jet will be proportional in some way to its transfer momentum. So let's try to estimate the distribution in perturbation theory. So the easiest thing we can do is to do an order alpha S. So now comes handy what we've done so far. What is the background? In the background, I have to produce a Z recoiling against a jet. That's precisely the type of diagrams will be computed for Drelian. That's why we built from Drelian. Now, if you go to order alpha S, so for instance, we take this guy, this order alpha S. What is the mass distribution of this jet, of the jet of this order? Zero, okay? Because at this order, the jet is made up of only one parton, and so its mass is zero. So we have to go one order higher to do the calculation. And so we need to consider, for instance, this type of final patterns. And we would like these two guys to be reconstructed in the same jet. And so really, the calculation we have to do is order alpha S squared. Let's try and write down these type of contributions in the collinear limit. So in the limit where this invariant mass is zero, is small, so this propagator goes on shut. So what does it look like? Well, so I want to estimate, I want to be differential in transfer momentum of the jet, and I want to look at jet mass distribution. I divided out the, I call it sigma 0 is not appropriate because here is really like the cross section for Z plus 1 jet. So let me call it just sigma. Sigma 0 is put in the position. So in the collinear limit, we know, we can use factorization, so we know what does this guy look like. Well, I'll have alpha S over 2 pi. If I look at this type of contribution, I have CF because the color factor for the emission of a gluon of a quark is CF. And then I have my phase space in the collinear limit, dz p. So this is a time-lag splitting. So in the time-lag splitting, this guy is called PGQ. It's a name, it doesn't matter. And then so in principle, this goes from 0 to 1. And now I ask myself, what are the limits of the theta integral? Well, I want this guy, the 2, to be reconstructed in the jet. So this should go from 0 to the jet radius. Almost done. Now I want to, so this will be the total cross-section, which by the way will be divergent because when I go fully collinear, then I will have to add the virtual correction. But here I'm going to do something different. I want to measure the differential distribution in the mass. So I have to require, I want to do this integral, keeping fixed the value of the jet mass. So the jet mass should equal, what is the jet mass of this pair? We calculated before, is Z, 1 minus Z, theta square, PT square. That's the same calculation we did before. now I can tell you that if we're interested in the logarithmic, so PQG is divergent in the soft limit. So PQG is 1 minus z squared divided by 1 plus 1 divided by z. So it's also divergent in the soft limit. It's divergent in the limit where the momentum of the gluon becomes small. And so if I'm only interested in the singular region, I can further simplify the expression and I can drop this z. So in other words, I'm interested in the region where z is small, and so 1 minus z is almost equal to 1. So I can drop this contribution. Okay, so let me do this integral for you. We first use the delta function to do the angular integral. Okay, so I have alpha s over 2 pi CF. If I use the delta function to the angular integral, I get the 1 over theta square gives me 1 over mj square. And then I have to still integrate the splitting function. But now I still have I have another condition. So remember the integration limit of theta. So theta square had to be smaller than r square. Okay. Now I did the integral of over theta with the delta function, and the delta function fixed.
Unfortunately, there is the break, so it's
yeah, no, but it happened to me also during like normal lectures, and then you feel a bit embarrassed.
Okay, now it's 11, so I guess we can start again
and then finish off the calculation. Well, I mean, it's not a difficult calculation, so I'm sure that any of you could do it. Okay, so we discussed like we see that we have to introduce so we introduce this bound. Actually, this bound is very important because you see this bound is what saves is what is going to shield the singularity as z equals to 0. This is the fact that this bound exists is a manifestation of IFC safety of our observer. Okay, it means that we can do all the integrals and the observer regulates the singularities. Okay, so we can do this integral. That's not a technical integral. So this alpha s CF over pi 1 over mj square. And then let me break the integral in two. So I have the integral of the singularity PTR square and 1. And then I have the remaining part. So I simplify the 2 because I get you are theoretical physicists, so I don't have to explain all the steps. And here what I have minus 1 plus z over 2. And now in this integral, I can actually remember I'm interested in the limit where mj over pt is small. That's boosting. So I can put here 0 safely, and I can say that this result is correct up to correction of mj over ptr square. So it's correct up to power corrections, which again, anyway, I don't control the community. And so I do now this integral. The first term is a logarithmic contribution, so it gives me the log of the ptr r square over mj square. And then I have a constant, and if you do this integral, you get the ranges. Remind you, we already encountered three courses. We call it V1 in the resummation for ZPT. So because I'm lazy and because it makes sense from the point of view of physics, I'm going to call this guy 1 over rho. So for me, the jet mass distribution is really a distribution in this dimension as parameter mj square over pt also. Now, as an exercise, you can repeat the calculation for different splittings. So, for instance, you can consider this guy. This propagator goes on shell. So in the limit where the two gluons are collinear, and you can put it also together with this guy. So in jargon, we say that we did the calculation for the quark jets, and I give you as homework the calculation for the gluon jets, the jets which have been initiated by gluons. You find a similar structure with a different color factor. So you get Ca as a color factor, and instead of -3/4, you'll find a different number, which is actually related to beta 0, coefficient of the beta function. So we are interested in the boosted regime, so in the regime where Mj is much smaller than PTR. In other words, we're interested in the regime where rho is small. And so we see that we're back to the issue where we face for the PT distribution of Z boson. In the region we are interested in, we develop large logarithmic corrections, because in the limit where rho is small, you see that this log could be large and spoiling your perturbative accuracy. This pattern repeats itself at high. So we need to do the resummation. We can use a very similar technique as the one we employ for the Higgs, for the ZPT, but here I want to give you another derivation. This is a lecture course, so we should look at things in different ways. This will be a bit more qualitative, but it gives you, I think, a good physical understanding of what's going on when you resum. So instead of doing the calculation as we did it before, we go for a more graphical interpretation. If you remember, and to do so, we have to restrict ourselves for the time being in the soft n collinear limit. Okay, and if you remember, I said it as a sort of an aside comment that if we look at the soft n collinear limit, QCD matrix element essentially have the form alpha s d theta over theta, d theta over theta, dz over z. And so these emissions in this double collinear, soft n collinear limit are uniformly spaced in a plane which is defined as the log. Actually, I think I put r and log of 1 with z. This is called the Loon plane. And in the Loon plane, if I go collinear, I'm going in this direction. And if I go soft, I'm going in this direction. This is one version of the Loon plane. Of course, any change of variable, many times we use instead of z, kt, the transfer momentum with respect to the jet, but it's just a change. At this point, it's just a change of code. So what is the jet mass? So let's imagine we have an emission here. So we have an emission in our jet, and the emission is characterized by some distance, angular distance with respect to the jet axis, or the half pattern if you want, and some momentum fraction z. What does the jet mass look like in this plane? So remember, in the soft n collinear limit, the jet mass, I'm going to drop the subscript j because I'm a bit lazy, look like z theta square pt square. So the log of the jet mass square is log of z plus log of theta square. And let me write this as r square, or r square plus log of pt square r square. Actually, maybe I'm plotting this. I don't know if it's relevant or not. Okay. It's the same, really, like you can rescale the variable as you wish. So and but I think for the drawing, okay. So let me rearrange a little bit this expression. So I have log of 1 over z is equal to, sorry, to the other side, is equal to log of theta square by r square plus log of 1 over rho. And I guess if I want to write the very same variables, I have to write it as r square divided by theta squared with a mass. So all points which lie on this straight line in these double logarithmic variables, they give rise to the same jet mass rho. So this emission, let me draw a jet mass. So all points that lie along this line gave rise to the same mass. All points which are all emissions, so points that lie above this jet mass, they give a different jet mass, of course, and this jet mass is infinitely smaller because remember this is logarithmic in space, so all the emissions that live in the all the emissions that live above this line, they give rise to emissions which are softer or more collinear than the original one. And so these points, they all have masses which are much smaller than this point I'm writing here. In the strongly ordered regime that we're interested in, if you want to capture the Lilith behavior, we say that all these contributions give a negligible, all these emissions give a negligible contribution to the jet mass. They change the jet mass only by a tiny little bit, so we can ignore. Instead, on the other hand, emission that lies here in this plane, well, they give a contribution which is bigger than the green emission contribution to the jet mass. Okay, so now we want to compute the jet mass distribution. When we compute the jet mass distribution, we have to assume, as we did before, there is one emission, before I only had one emission, that gives me the jet mass. This is the emission that enters the delta punch. So let's assume this is the emission that sets the jet mass. Okay, I can have any other number of emissions that lie above this, because these are not going to change my jet mass in a significant way. What I mean is that they're not going to change from the point of view of the logarithm of the jet mass. So I can have them or not have them, I don't care. They don't change the value of the jet mass I'm measuring. However, I cannot afford to have emission below this line, because these emissions will give me a different value of the jet mass. So they will belong to a different bin in my jet mass histogram, if you like to think about this. So if I insist that I want this value of the jet mass, the one identified by the blue line, then in my calculation, I have to veto any emission that belong to this blue triangle. Okay, so I cannot have emission there because they will change the value of the jet mass. Can I estimate the probability for this emission? Well, I can, and the way I'm going to do it is by using a simple argument that works in this double in soft and green limit. So let's imagine that I take my triangle. So by the way, these values are characterized by theta over r to be of order 1. So they're both sides, they both leave or z equal 1. So these points they're characterized with this by this one. Okay, so how do I estimate these veto bridge? Okay, let's do this exercise. I take this area and I divide it into n little squares. And I'm going to take one of those. I mean, here is pretty large, but imagine just so you can see. Imagine I do a very fine job. And I can ask, what is the probability to have an emission in this little square I? Remember, we are in the soft and green limit, so the probability for having emission in my little square I is proportional to the area of this little square. And so it will be in our convention alpha S CF, because it's a work jet over pi, proportional to the area of the jet. Sorry, to the area of the little square. What is the area? Well, if I taken the large triangle, which has an area a half log square 1 over rho, and I divide it into n little squares. So the probability for having an emission in this little square is given by this expression. And so the no emission probability P bar is 1 minus Pi, image square. Now I can ask myself, what is the total emission probability in the blue triangle? Well, assuming that the emissions are independent, I take 1 over n. I take I take P bar to the P bar I to the n. So I have 1 over n alpha s over 2 pi log square 1 over rho to power n. And then I take the limit in which I consider an infinite number, usually an infinite number of little square, in the limit where the squares become smaller and smaller. So I take the limit into it. And this is an exponential series, which gives exponent of minus alpha s over 2 pi CF log square. Which in a way, Jesse Taylor likes to write, this is the exponent of minus the area of the blue triangle. So this is a very simple, almost hand-wavy, fixed leading logarithmic fixed order derivation of a guy which we already encountered, the pseudo-compound factor. So that's why very often you read in lecture notes and textbooks that the pseudo-compound factor represents the no emission probability. And this is a very simple way to deriving, and but I think it's very physically motivated. So this is the way this is done a little bit more detailed in a nice review by Andrew Rakowski, which is called an unorthodox introduction to QCD. But it's powerful because it allows us to essentially relate areas on this Lund plane to actual calculation. Because you see, we exponentiated things. So now essentially, by coloring areas, so by doing kindergarten activities, we can write the double differential distribution of the jet mass. Actually, let me write it for rho, because we are talking about rho over sigma. Well, that's I want an emission that sets the mass. So this we calculated already. That's the probability for one emission. Let me do it for rho times sigma. So. And then I have my pseudo exponent. So believe it or not, this is the resummation of, it's a very crude approximation, but it gives us the resummation of the leading logarithmic approximation, or the leading logarithmic terms to the jet mass distribution. It's very crude. I wouldn't call this an actual thing that you compare to data, but it gives you a feeling of like the distribution. Can we take this and promote it to the same level of accuracy that of the calculation that we did for the Z boson, the PT of the Z boson? Yes, there are some steps you need to address. First of all, there are easy things that you need to account for. And I say easy not because they are actually easy, but because they are the same type of effects that we studied for ZPT. So these are the running of the coupling. Okay, here I worked in a fixed coupling approximation, so you need to have the running of the coupling in 2 loops. Maybe, well, I guess you can include the full splitting function. So you go beyond equilibrium limit, and the CMW scheme, or what other people call the two-loop anomalous dimension. These are easy in the sense that these are the same ingredients that we did before, so we could do the calculation. There are things that are a bit more difficult. But well understood. So really, when you do jet physics, you really have to worry about also soft gluons and large M. These are the guys that don't fully factorize in terms of their color connections. And so for ZPT, you can actually get away without it. But here, we really have to account for that. And they can give rise to a very non-trivial structure in terms of matrices in color space. So, soft gluons, a wide angle. What is interesting here is that, which have non-trivial color factor. What is interesting here is that we can say something about these contributions. So soft gluon and wide angles give rise only to single logs. And we can actually write down, before doing any calculation, what is going to be there for. So there will be a very complicated color factor. This won't be a CF or CA because you can, when you write it like that, because you remember, we can connect, we have a matrix structure. They are single logs, so alpha has to be n log n minus 1 log rho times 1 over rho. And then there's a function in front of them, complicated, you need to do the integral, but which can only depend on the jet radius square. Just to be clear, what this is, that contribution I have in mind that, for instance, this one's right. So you have, you can have a gluon in the initial state that then is reconstructed in the jet. No collinear singularities, but soft singularity. This function f has an interesting property for soft emission and wide angle, starts at order r squared. So one way of dealing with this soft gluon and wide angle is to treat them in treat them in what is known as the small radius fluid, and so computing them as a power expansion of jet radius. That's a calculation trick there sometimes. And last but not least, we also have very difficult things. And here there are two categories of difficult things, very difficult things. One is called, and they all have to do with the fact that at higher order we can have more emission that combine in a trivial way. So the first one is called non-global logs. And non-global logs are configuration for which you have your jet, and you have maybe a gluon, soft gluon, which is emitted outside the jet, but the gluon splits an even softer gluon inside the jet. Believe it or not, these contributions are a nightmare to resolve because they don't exponentiate. And these are still a very active area of research. Very recently, there was a paper by Pierre Monni and Andrea Banfi where they managed to actually compute correction to this type of contribution. But these are very difficult, and typically they resound numerically because there's no clear way of organizing them into an analytic expression. So usually one resort to the large MC limit or things like that. And related to those are, so these are non-global logs. Related to those are the fact that at some point you become also sensitive to the jet algorithm that you use to identify your jets. So if you have only one gluon, I told you that the gluon is either inside or outside the jet depending on its distance. So if it's a distance less than r, is inside the jet. If it's a distance bigger than r, it's outside the jet. Now, if you have more gluons, this can be complicated. And in particular, things remain simple for the anti-KT algorithm. But if you want to use, say, Cambridge-Aken, then things all of a sudden becomes very complicated because the clustering algorithm can, for instance, cluster together two gluons first. And then the clustering algorithm will ask whether these gluons go into the jet. Now, again, this is difficult to implement in analytic calculation. And that's why most of the resonation for jet properties are done with the anti-KT algorithm. Because if you still want to use Cambridge-Jack or KT, again, you have to deal with these type of effects, which you usually deal with numerically. So all these three ingredients are possible to achieve to some degree, some of them only numerically. And if you do all the three, if you address all of the three, then you reach the same, then you reach the resummation of the jet mass distribution and nested in log accuracy. Okay, so calculation for jets are way more complicated than calculation for the ZPT. There we can reach n-cubed LL approximation accuracy. Here we struggle with nested in log. Some of these ingredients are known at high orders, but not all of them. And that's why we are, it's more difficult to achieve precision for this type of result. Okay, so, but we can, so let's go back to our original plan. So we want to understand what is the, remember, we want to understand what is the jet mass distribution for the background. And now we found it. So it's an exponential modulated by this first emission contribution. So it's if you plot it, it has a pseudo-comfort factor and then a tail. Okay, so where is this peak? Well, this depends on the value of the PT we're looking at. But we can hope that this mass peaks at a different way with respect to the signal, and so we can actually distinguish this distribution. Remember, this is what we want to do. We want to look at distribution and try and distinguish. However, you know, things are complicated because the position of the peak depends on the PT you're looking at. And so you can get also background mass distribution that peaks near the X mass. Moreover, there's another effect. I mean, this is a simple Platonic calculation. When you try to embed this in a more realistic simulation of NLHC events, all sorts of things happen. The handleization process, the underlying event process, so more multiple parton interaction for every proton. And also we mentioned pilot, so the fact that you have multiple interaction, multiple proton interaction per punctures. All of these spray soft radiation into your detectors, and so distorts this simple distribution. So really, when you try to look at the simulation, which is a bit, say, more realistic, you'll find that the single jet doesn't look very sharp. The peak of the single jet doesn't look very sharp anymore, but more typically will be you know, still maybe peaked at the Higgs, maybe shifted, but fairly broad, something more like that. Typically, all these distributions are shifted because they're, you know, if you put stuff into your jet, the environment mass tends to increase. And similar, very similar for this guy. So this will be distorted, something like that. So when you add this soft radiation coming from underlying event, transition hadron to particle, the underlying event, and pileup, you distort your signal and background jets to the point that it's kind of difficult to reconstruct this idea of like, I want to see the peak and I want to project it against the background. So that's when actual jet structure comes into play. What we would like to do with jet structure techniques is sort of take, okay, we take a particle level event, so the one which has been polluted by all these effects, and we would like to bring it back to something that looks a little bit more partonic. Okay, we want to do this in a safe way, of course. So we don't want to just say, you know, I stopped the simulation at parton level and no, I want to say for something which is experimentally relevant, and I want to try to do something to my events so my distribution, they resemble more closely the partonic degrees of freedom. And so I want to find a way of eliminating this soft pollution from my jet. Once I've done that, this is the first key concept in jet structure and goes under the name of grooming. When people talk about we want to groom a jet, that's what they mean. So they want to identify some they want to resolve the jet to a smaller angular scale, and by doing so, remove what is soft in the jet, so that I'm hoping to bring back the jet to a more pattern level type configuration. So when people say grooming, that's what they have in mind. An algorithm that tries to get rid of pollution in my jet and bring it back to something that is closer to my naive platonic picture. Once you've done that, then you can do tagging, which is the second buzzword in jet structure. So once you have your jet that looks more like a platonic jet, then I can try to find some feature which is shared by which is present in signal jet, but not shared by the background. And one example of tagging actually we already encountered. So remember I told you that if I have the Higgs to BB bar in the collinear limit, so in the limit where this angle is small, this is proportional to the splitting function for Higgs to BB bar. And that's essentially 1. It's constant in Z. On the other hand, if I have this type of splitting, 1 minus Z, the splitting function is proportional to 1 over Z. So signal jets will be characterized by a symmetric sharing of the energy. Background jet will tend to have something hard together with something soft. And so if you're able to bring back your jet to something which resembles this platonic configuration, then you can do tagging. What does it mean? You can impose a cut on your jet. So for instance, you can ask that the minimum between Z and 1 minus jet should be bigger than some threshold Z cut. And in this way, you reject the background and you keep the signal. But this will be useless if you didn't do grooming, because if you look at your jets and these are, populated with a lot of junk, which comes from something which has nothing to do with the Higgs decay, then this tagging procedure will be very inefficient. If you want to do efficient tagging procedure, most of the times you have to do. And actually, most of the times, the vast majority of just structural algorithms, they do a little bit of both. Okay, so in the remaining half an hour of my lecture, I want to give you 2 examples of this. And I'll try to be rather quick. So the first example is an example of grooming. And dear to my heart, for many reasons, a particular type of grooming, which is called the soft drop algorithm. That's something that we developed together with Andrew Lakowski, Jesse Taylor, and Gregor Soyer. And faithful to its name, soft drop drops soft radiation. So how does it do that? Well, the actual working, it's a bit complicated, but the idea is that, let's say we have 2 branches in a jet, and we want to compare them. And the 2 branches in the jet, they have transfer momentum PT1 and transfer momentum PT2. We compare these 2 transfer momentum. So we look at the minimum of the 2 and we divide it by the total. And we ask ourselves whether they are bigger or smaller than an energy cut parameter and an angular distance in the azimuth rapidity plane to some power beta. If this condition is satisfied, it means that there is some that the 2 guys equally share the energy weighted by some angular exponent. And so if this is satisfied, we keep this jet and we call it a soft drop jet. If this condition fails instead, we drop the softer of the 2 from the jet. So this seems like a condition, like, you only check this condition once. Actually, what we can do is that we can apply this recursively through the entire clustering of the jet. So you can imagine, start from your jet and recluster with the QCD motivated algorithm. Say, for instance, you start with your anti-KT jet and recluster with Cambridge-Aken. And this allows you to build a jet which has a clustering history which is ordered in angle. So for instance, your jet in this representation may look like that, something like that. Okay, so what do I mean with this? You see that these, when I I order my jet, my clustering history with Cambridge Arcane, and then I go back one step. And if I go back one step, my jet is made of 2 branches, 1 and 2. And these 2 branches are the ones which are mostly separated in it. And I apply my software condition and I ask, is this condition satisfied? If this condition is satisfied, it means that there is a balance. This jet is made up of some of hard stuff. In particular, it means that this splitting was hard. So if this passes the software jet, then we're happy. If it fails, let's say the 2 is very soft or a large angle, so this condition fails. So I remove this guy and I iterate on the remaining part of the jet. And then I ask, I have 2 jets, this guy, 2 subjects, this guy and this guy, and I ask again the same question. And in this way, I recursively groom away things which are either too soft or a wide angle with respect to the core of the jet. And I get a jet which is more resilient against the soft physics, which I don't understand. The interesting thing, I mean, when SoftDrop came out, there were like a plethora of other tools on the market. Why this became somehow more popular in this business? Well, it's because we can reach a very good analytic understanding of what SoftDrop is doing. And in order to do that, we can use, again, the Loom plane. So you can plot the SoftDrop line, so the line that describes this inequality, the one which describes the equality, and it turns out that the SoftDrop line is something like that, if beta is positive. And what SoftDrop does, remember, in the Loom plane, this region here is soft. And indeed, what SoftDrop does, it removes in a safe way from the jet this area. So emission in the jet that happens here are groomed away. And by the way, you can even lower beta, you can have beta equals 0, this would be something like that, and you can have also negative beta. And now we can play the same game. Can we compute the jet mass distribution for a jet which is undergone soft drop? Well, we play the same game as before. We identify an emission that sets the mass. Let me get rid of these because they're not relevant anymore. And now I do the same thing. Since I like kindergarten, instead of doing the calculation, I color things. And you see, this picture already immediately tells me that I'll have a pseudo-comfort factor, which is different, because now the pseudo-comfort factor is this blue area. And in particular, the pseudo-comfort factor is not sensitive to the soft region. So I built a jet mass distribution which is robust against soft emission. It doesn't care about soft emission. And I win because I get softer jets which receive small contribution for non-perturbative stuff like the underlying event and tie-up. Actually, this came as a surprise, but then it was realized they also have reduced hadronization corrections. And so I get something that for which perturbation theory is more reliable. And this came as a surprise because I do something quite elaborate on my jets. So I apply an algorithm which is fairly non-trivial. However, at the end of the day, I get something which is more calculable than what I started with. Something for which perturbation theory is more robust. There's actually something more. This is specific for soft drop. The way it's constructed gives me something for free. So for instance, this complicated, very difficult thing I mentioned, so non-global logs, color correlations, they either vanish for soft drop jets or are very much reduced. And for this reason, actually, we know the soft drop mass distribution, soft drop, we know it at n cubed leading log. So we know it much better than we know the normal jet mass distribution. Because we essentially can get rid of, in a safe and controlled way, of complicated structure due to self-prediction. And this opened up a very new possibility in using gesture structure. So gesture structure was built and is still being developed as a tagging technique. So we want to discover, we want to study the Higgs, or we want to discover in physics. So that's why people start thinking about this type of tools. But actually, we realize that some of these tools are good for calculation. Well, the calculation for some of these observables are easier. They can be done to a higher accuracy than before. And so we can now think about using this type of algorithms also for standard model physics or precision physics, because we understand, we control the distribution in a better way. And this sort of like led us to sort of like to people really start thinking about gesture structure techniques in a kind of like a two-dimensional way, right? So here I have all my structure techniques like soft drop or other ones, right? And but in order to make improvement, I have to go into two directions. I have to build tools which are efficient. Of course, you know, if my tool cannot, my algorithm cannot distinguish signal and background in an efficient way, I don't know what to do with it. But at some point, by doing this type of calculation, people realize that there's another dimension. So I want to build algorithms which are also robust. And robust means that I understand their behavior with the tools I'm familiar with. So perturbation theory, for instance. I understand how they depend on non-perturbative corrections. I understand how they depend on the parameter that enters this scheme. For instance, soft drop throws in two new parameters in your calculation, Z cut and beta. And the more parameters you have in your calculation, the more messy your calculation. The people really exploit, theorists really exploit their QCD understanding, their knowledge of the understanding of physics, to build tools which are efficient and robust. And on the other hand, together with experimentalists that were able to actually realize in reality these algorithms, thanks to fantastic development in the way they understand and they use the information from the detector. And all of these cannot be possible with physical intuition and imagination, because you need to think something new, something out of the box. And in the, gesture structure is a field which has 10, 12 years, and hundreds of ideas have been developed. Some of them, I would say tens of them, have been actually translated into algorithms which are publicly available. The best way of getting your hands dirty is to look at the FastJet country webpage. And some of these are, many of these are actually used by the experimenters. Okay. So if I was doing these lectures 3-4 years ago, I would have stopped here. However, I think in the last 15-20 minutes, there is one big thing I need to really talk about, or at least mention. And it's the fact that in the past 5 years, there's been an explosion of application and development of artificial intelligence, or called machine learning algorithms, to physics in general, and to jet physics in particular. And examples, so let me call it in general neural networks. Neural networks have been used for a long time in particle physics, but really, it's really in the past, say, 5 years, that tremendous development that happened outside physics, like in a community which is not our community, which, for instance, has to do with deep network or other developments, unsupervised, and so on and so forth, allows us to sort of extend the range of application of these techniques into particle physics and develop new. And nowadays, neural networks, modern machine learning algorithms, are using a variety of contexts. So, for instance, if you think about jets, this jet classification. So answering the question, is this a signal jet or is it a background jet? Turns out the machines do much better than us in theories. Okay. Challenging still. In the context, something I mentioned, in the context of the things which is called B tagging. So try and understand whether your jet contains B hadrons that originate from B quarks. In the context of BSM, there are many people active on this anomaly detection. So I have a large data set. Can I find something anomalous in my data set without like biasing my analysis with the particular BSM process? Again, in the context of jets, another thing I can think of is pileup subtraction. This is also done using a lot of machine. So I want to take my events and try to clean it up, removing this stuff that comes from a different proton-proton interaction. Something that we mentioned, and this actually has been going on for a long time, but recently completely redesigned in light of the new developments in machine learning, is fitting, so determining pattern distribution function from the data. There's a big collaboration that's been doing this for almost 20 years, and which is called the NN-PDF collaboration. And very recently, they actually redesigned the entire framework to exploit new techniques. What am I missing? Well, okay. In a more theorist interest, you can use these things to actually improve the way you integrate your matrix elements. That's another thing which is quite interesting. And what I want to say, and this I know nothing about, but I think it's quite fun, event generation. So you can use these, they're called adversarial neural networks, so two networks that compete with each other to try and not use just for classifying events which are being produced by nature or by another simulation, but actually to generate events. And that's actually very interesting from the point of view of simulating detector response. That's usually a very expensive thing to do, to try and see how my physical signal is then distorted by the detector. And there's been a lot of progress. In the very final part of my lecture, I want to give you one example of this technique in the context of jet classification. And these are called jet images. So let me go back to the picture, proton-proton collision, something happens, and then the debris of my collision, they're collected by the calorimeters. The calorimeters are some sort of cylinders which are wrapped around the beam. And in particular, we focus on the hadronic calorimeter. And so you have, we said that we have mostly jets, right? And so this collision produces some hits in the hadronic calorimeter. Now we imagine to cut our cylinder and open it, unroll it, and that's how we obtain the azimuth. Well, here you can put rapidity, pseudo rapidity. We have theories, so we put rapidity. Well, I mean, if you really open the detector, this will be the pseudo rapidity, but you can translate. And so you can represent the hits. Say maybe you have a hit here, a hit here, very energetic. Then you have a less energetic hit here, maybe one here, maybe one here, and so on and so forth. And you see that these the fact that these calorimeter cells are lit up by the interaction, they form some sort of pattern, and that really look like pixels on an image. And so the idea that people had, like 6 or 7 years ago, is to say, well, can we use techniques which have been developed for image recognition by, I don't know, Google or other big companies, and use them to distinguish images originating from signal jets and images originating from background jets. So in our context, is this image coming from HDBaseT bar or a QCD jet? And so people said, well, okay, the best way of doing this, we're told by our computer scientist friends, is to use convolutional neural network. That's a particular type of neural network. And we asked, so if this network can distinguish cats and dogs, can it distinguish pigs from QCD? And it can, with some current. But this type of algorithm have been applied at the LHC, and they show to outperform all the clever ideas that theorists had in this business. What are the caveats? Well, I can think of many. First of all, these typically event at the LHC, they produce very sparse images, and so that's why, you know, particle physics only makes sense if you collect many events and you average over them. We build distribution with millions of events, and so we would like while a picture of a cat is a picture of a cat, you don't have to average. It's one thing. How do you do that? Then also another difference is that, well, you know, if you see a picture of a cat, you immediately say, well, that's the cat is upside down. If I show it like that way, here it's not clear. Like I want to, you know, there's the symmetry, the internal symmetry in my theory, and so I cannot simply add all the images that I get and average them because I've washed out all the information. So I need to do some pre-processing. So I have to make sure that when I take the average, I always locate images in the same way. But if you do so, and then people worked hard on this, the results are really spectacular. And machine learning classification algorithm, they outperform the things we discussed so far in a fantastic way. And then, so first reaction for someone who, you know, spent quite a few years of their career working on this, the question that comes to mind is that, should I be happier set? And I think it's a bit of both. You can be sad in a sense that, like, indeed, like, this machine do better than anything your mind can come up with. But happy also because there are new possibilities, and even happier if you can find a way to sort of like understand a little bit better what is the type of information that these machine learning algorithms are exploiting. And let me give me a quick example of that. So let me first remind you, I mean, I'm not expert in this, but let me just remind you how this works. So how does the neural network learn how to distinguish these things? In the simplest possible case, these are the sort of like, it's called supervised learning. You essentially have to teach the network what to do. So you prepare samples, which are signal samples, a background sample, and you pass them through the network. What is the network? The network is a collection of neurons, and neurons are essentially something that perform an operation. So a neuron takes some input, x1, x2, xn, and performs some manipulation. Typically, what it does is that it performs a linear combination of the inputs with some bias. So let me. And then also a nonlinear part. So sometimes, like, I don't know, for instance, f could be the sigmoid function. 1 plus. And So then there are many neurons in the network, so all of which does this all of which does this operator and then pass it to the next layer. And this A and B these are parameters of the network. So at the beginning, they're just like essentially random numbers. And at the end, the network gets an output. Let's call it Y. And what the network does, it compares this output with the true label. Because remember, I'm doing supervised learning, so I know whether the inputs came from the signal of the vector. And it evaluates the difference between these two with some function, which is called the cost function of the loss function, and then goes back and tries to minimize the parameter of the network, the A's and the B's, so that this difference is minimal, so that the loss is minimal. And it's not very, and he does this over and over again, so that it gets like the best possible set of parameters to classify Simone. Now, the question, the interesting question I want to ask myself as a final question of these lectures is what should I pick as inputs to my neural network? In the jet image, I pick a very low level type of inputs, namely the cells, the amount of energy that is deposited in a kilometer cell. This is low level in a sense that like it's what I measure. There's no, you don't need quantum field theory to measure the amount of energy in a cell of the calorimeter, and that's what I give to the neural network. Or I can be a little bit more clever and I can reconstruct the particle for momentum. I will also call that low level because again, there's not a lot of like theory. On the other hand, and that's why I think there's something possibly interesting for theorists to give a contribution on, is to say, well, what if I use instead something which has some theory information, something which I call a high level. In other words, would it make sense to feed the neural network not low-level quantity, but some theory-inspired variables? So can I exploit some of the expert knowledge I have in the field as inputs, to design inputs to the neural network? And here, our understanding of the physical process at hand comes into play, because quantum field theory provides us with a very good understanding on the underlying physics we're trying to we're exploring. So, for instance, we understand the symmetries, we understand the splitting patterns, and so maybe we should build in our inputs and in our architecture. This I explore less, but that's also very important point. My architecture and my inputs should reflect the knowledge I have of the field. Of course, this is a risk because I may bias the outcome of the network, but it's a very open question. It's what Jesse Taylor calls deep learning meets deep thinking. We spend decades in designing and understanding our theory, and we have something which is quite unique because machine learning applied to social scientists or even to other natural sciences like meteorology, they lack this possibility. We don't understand social science at the same level of accuracy at which we understand QED. Okay, so maybe there's something there that we can exploit to understand what is the network learning. There's no question that the network is doing a better job than what I can design. But why is that the case? And what is the information? Is this information the network gaining? Does it lie in the perturbative domain? So can I understand it with quantum field theory, or has something to do perturbative quantum field theory, or do we need some non-perturbative theory to understand it, or is I don't know, even more difficult? So in the final 3 minutes, and this doesn't give me any justice to the topic, but I'll try to illustrate one example. And the example has to do with, again, with the loop plane. So we build the loop plane, we use the loop plane as a way of performing calculations, essentially, okay? And here, I'm gonna write it in terms of, it doesn't matter, but like, in this context, it's usually plotted with KT, not Z, but that's not an issue. So a few years ago, Frédéric Dreyer, Gavin Salam, and Gregor Soyer, they had a fantastic idea, which is, well, okay, let's turn this calculational tool into an observer. So how do we do that? Well, again, we reclassed the Cambridge Jacket, so we have a QCD-friendly history of the jet. And then we, again, in the same way as with subdrop, we go back in the clustering history. So, we undo the last step, the jet is made up of 2 subjects. But this time, instead of like throwing away things, we record the kinematic of each of these clusters. Okay, so you go back and you say, what is the relative Z and what is the opening angle? And I store this information. And this information ends up to be a point in the limit plane. And then I do for another one. And then I go through the clustering history. And maybe there are 2 clustering that happens in the same, so I can actually give some coloring to this guy. And I can do this in many ways. I mean, I can only follow the hardest branch every time, or I can do everything. So if I do the first, I build the primary. But details don't matter, but you see what I'm getting to. This looks like an image, but it's no longer a calorimetry image. So the axis, these pixels are not calorimetry cell, but they are high-level information which I extracted from a theory-inspired observer. And so I have a representation of the jet, which is not the image of the calorimeter, but is a representation in terms of variables which I understand, variables that are dictated by QCD evolution. And so I can do things. I mean, I can actually compute the density of these points on the loop plane. That's something that these guys did. I can measure this plane in experimental analysis, and that's what Atlas did. Or I can take this image, many of them, and feed them to a neural network. And I can use this image in the same way as I use calorimetry image. I think the jury is still out whether, for sure, the fact that I can calculate the density and measure at the LHC, it's something interesting. And I think the jury is still out whether this is better in terms of identification classification properties with respect to, say, calorimetry image. And of course, like the answer to this question really depends a lot on the architecture that you exploit. Yeah, you can use simple convolution neural network, or you can do something even more fancy. But the point is that you throw something new in the game. You use something that is QCD motivated as an input to the to your neural network. And on the other hand, but I don't have time to, and also I don't have knowledge about this, you can also try to build your architecture in such a way that respects the symmetry of your theory. Some of you the other day mentioned Lorentz invariant network. So I think I should stop here. I was hoping with this very last half an hour to give you something which is really is at the edge of the frontier of research in collider physics, and in particular jet physics. And I think, well, I hope I tried to convince you that it's, I managed to convince you that it's, there are challenges ahead. And probably the way we thought about these type of topics in the past 10 years, which has been, I think, very successful, will have to change a little bit, because we have a big elephant in the room. We have algorithms that do spectacularly well, but they kind of sometimes are treated as black boxes, and they kind of a little bit outside, I would say, the comfort zone of the average theorists. Some theorists embrace this in a full way. Other theorists, and I think the majority, are a bit skeptical, but I think it's this idea of like try to see if theory-inspired variable can teach us something about what the network is learning. I think it's a very interesting and challenging question for the future. Okay, I think that's it. I hope I managed to convey something interesting despite the distance. And I'll be happy to discuss it more this afternoon.
Thank you very much, Simone, for this nice comprehensive course. Are there questions for Simone?
Yeah, I'd like to ask, what do you think the main bias of using the Lund plane would be as opposed to calorimeter data?
Interesting question. No, I don't. So I think so I was. I don't know. So I don't think that I don't see the bias the most. So I was putting there more as like an open question, something that may we may a crisis that we may have to face. Let's put it this way. Maybe so when you build a calorimeter image, I guess it would be, so for the loop plane, it would be difficult to, okay, I have to think about it. Let's say to distinguish things that look a lot like QCD from QCD itself. This might be also the same for the calorimeter image, but the fact that I build the loop, so the fact is, for instance, I choose the split, the kinematic splitting, the way I choose them, this has to do with the fact that my brain, I want to, you know, I know how the background behaves, and I kind of know how the signal behaves, so I want to separate them. If I add something which is a little bit closer to QCD than the Higgs gain to BB bar, these might be a little bit of a bias. This is the, I don't know, the worst case scenario. Now, this can also be the case for the calorimetry image, but since I know them less, I put like I make less choices which are detected by physics, I think. On the other hand, I do make choices. For instance, this pre-processing, and so yeah, I don't know how to quantify that bias.
Maybe do you have like some sort of heuristic for what type of information we're losing by moving to the Lund plane, or maybe something like that? Because essentially, anytime you do calculations over the experimental data, then you're introducing a bias. I'm not sure there's a way to avoid that.
So you mean, so you're worried about the fact that I take, so, okay, let's, would you say that like using 4 momenta would be a bias? Or let's you know, because we should pick a starting point. Okay, so if you have 4 momenta, well, okay, I see your point. I mean, the Lund plane is has a lot of construction to that. I need to build jets, and out of this jet, with these jets, I need to build a cluster history, and then I step backwards in the cluster history. So I can see that, you know, there are a lot of steps that I'm doing, and the fact that I decide to do those steps may bias my the outcome of my. Well, I don't know if it will bias the outcome of my classification, but definitely will shape what I'm going to see. So, because you can say, well, why did you choose Cambridge Avenue? You could have used something different. Now, if you look at calorimeter cell, you don't do this. I mean, someone built Atlas for you, and these are the cells are there. There's nothing else to discuss. So, in that sense, yes, I agree. There is some. There are some choices that are made, but I think so that's why one should be aware of this. But on the other hand, you build in things that you think you have, well, for which you have a quantitative understanding, and that's something that so I don't know. I don't have like a definite answer. I mean, this is really research, right? So I think there is value in using things that using observables that we have good control. We don't have good control about the energy which is deposited in the calorimeter from a theoretical viewpoint. but we have a good control about how the learn plane is formed. This good control is dictated by our understanding, so in that sense it's biased. But it's so I think one should do both. But if you want, I think if you want to understand the type of information the network is exploiting, for me, you need some theory input. But I mean, I'm thinking about it. Right?
I completely agree with you. Like, given a finite amount of computation, even just like from a working point of view, you'll never be able to work with the full parameter space. You have to truncate it somehow. And, I think this is a very interesting approach. I'm just trying to understand its limitations.
No, absolutely. I think this is the sticking point. So it's a and here we reach like an active area of search side. I think all. I mean, in some sense, the solution is in our and in your hands. So we have to find out.
Thanks.
But let me just conclude with the. So I'm optimistic. Oh, I don't know what I don't know what the aim should be, but the I think I think theory has something. Will I still have something? Maybe in a different way. So when people start working on this Grumman and targets, I remember going to this Boost conference, which are where people doing this the things meet usually, and I could remember the summary talk of say 2011, 2012. I'm not going to say the exact date so you don't know the speaker, but a very famous speaker said like, okay, all these grooming and tagging techniques are very nice. They work, so we can distinguish tops and W and Z, but we are giving up our ability of performing calculations in QCD because these arguments are just too complicated to do calculations. And this was proven wrong. And actually, these arguments, once you understand how they work, they improve your ability of performing calculation. So I'm not saying that this will happen again for machine learning, but maybe something similar can happen. So maybe if we understand better what is the type of information that these arguments are exploiting, maybe we can do back. We can feed back this into our understanding of theory. Actually, I think I read recently something that Jesse wrote that is not that we should try and also as theorists start thinking a little bit try to understand how the machine are thinking, and see if we can if this can influence our way of addressing it. Maybe I'm misquoting him. I don't know.
Okay, Simone, thanks for the discussion. I think that for additional questions, we can